So this is Ian Grooms. He is visiting us from the Courant Institute, and where he works on problems in parameterization and superparameterization of unresolved turbulence in geophysical fluid dynamics. He got his bachelor's of science at the College of William and Mary back in 2005. He's not quite that old. He's actually younger than I think. And then went on to the university, or it's Colorado University?
It's
University of Colorado at Boulder. Got his PhD in 2011. And now he's a postdoc at the Courant Institute at NYU, working with Andy Maida and Schaefer Smith. His original degree was in mathematics, and his PhD is in applied mathematics. And his PhD actually won an award to recognize an outstanding dissertation that directly contributes to nonlinear geophysics from the nonlinear geophysics section of the AGU. So this is a man with a lot of talent behind him. So please welcome Ian.
Thank you for the introduction. Thank you for inviting me. Pleasure to be here. So I'm going to talk today about a paper I wrote with Louis-Philippe Nadeau and Schaefer Smith, LP. Louis-Philippe is now a postdoc at MIT. He was my office mate at NYU. We wrote this, it was just published in the past year. The paper has the same title, and it's available on the webpage or from JPO if you're interested. So I have quite a bit of introduction and motivation. You can see at the top here, I have a lot of slides of motivation. And this is the first one. So as you may know, the 5th assessment report from the Intergovernmental Panel on Climate Change is sort of in the process of coming out right now. The physical science basis came out first. That's the cover of it. And it relies, in some ways, fairly heavily on simulations of the climate system. Atmosphere, ocean, ice, bio, etc. And in these models, it's impossible to resolve all of the active dynamical scales. We have small-scale weather systems, small-scale jets and eddies in the ocean. These things are not resolved in the simulations. And so you have to represent their effects somehow without actually resolving them in the simulations. This talk is going to relate to simulations, climate simulations, where ocean mesoscale eddies are not resolved. I'll go into definitions of what I mean in a minute. Just to convince you, though, here's a slide I got from Baylor Fox Kemper, which shows the grid scale of the ocean component of the coupled climate models from the IPCC reports. So the first assessment, second, third, fourth, fifth. This is the one that has just come out. The grid scale is up here, and then time is going across the bottom. And the blue band is the mesoscale range in the ocean. And as you can see, none of the models yet have even come close to resolving these scales. Some of them do not resolve these scales at all. Most of them are sort of eddy permitting, is what we would say. And you can extrapolate the trend across here. The black line is the fit to the median resolution. And when it crosses this line is when we'll be resolving mesoscale eddies fairly well in the global ocean in coupled IPCC class models. That's about the year 2040. So we have at least a couple more decades before half of the models resolve that range of scales well. So it's an important problem to study these dynamics and understand their impacts and their relationship with larger scale dynamics. Okay. Let me, just so that you are not misled, state that subgrid scale parameterization is an important motivator for our work. I'm not actually going to develop a subgrid scale parameterization. What we're going to do is study these eddies and study certain properties of theirs, and then comment about implications for parameterizations at the end of the talk. And then further development is something that we're continuing to work on, and other people are continuing to work on, of course, as well. What do I mean? What are mesoscale eddies? I've given you a scale range, and that's about it so far. Well, mesoscale eddies, for the purpose of this talk, are defined just by being at a certain scale, a certain physical scale. So it's not just these coherent vortices that you might think of when you think of an eddy, you know, a Gulf Stream ring or a Gullhaus ring or something like that. It's any dynamics, any feature that occurs on a scale near the Rossby deformation radius in the ocean. I'm going to assume you know what the Rossby deformation radius is. So that's mesoscale eddies for this talk. The title of my talk is Mesoscale Eddy Energy Locality. What is energy locality? So you can imagine eddies and eddy energy as being generated, dissipated, and fluxed around from one place to another. Okay, so the budget of eddy energy is generation, flux, and dissipation. This term is, of course, the flux divergence, but I abbreviated it with an F so that I could have GFD, for geophysical fluid dynamics. And what do we mean by energy locality? We mean that a region, a patch of ocean, has a local energy budget if generation balances dissipation in that location. So that the region may be importing or exporting some amount of energy, eddy energy, but the net budget is primarily a balance between generation and dissipation. Okay. Why does it matter? Well, it matters for parameterizations. Almost all existing mesoscale eddy parameterizations are local, in the sense that they try to relate the effects of eddies in a given location to the properties of the large-scale flow in that location. And the properties that are being parameterized are tracer fluxes, momentum fluxes, things like that. So it's not exactly the same as energy locality, but they're connected. Energy locality, or energy non-locality, actually, would suggest that local parameterizations might not work so well. So a paper written by Baylor Fox Kemper and I believe Scott Bachman, S stands for Scott, I think, recently 2013, ran some eddy resolving high resolution simulations in an idealized setting and diagnosed the eddy fluxes and compared it to existing parameterizations, existing local parameterizations. And they found that you get a fairly poor fit. You get about a 97% error bar using existing local parameterizations. I don't expect you to understand this full quote, but when you, instead of doing a local parameterization, you just diagnose the local eddy kinetic energy and then plug it into an existing parameterization, you reduce the error bars down to about 28%. And their conclusion here is that the situation in parameterizations would be improved by using a non-local form of parameterization, which would mean that you would carry around an equation, a prognostic equation for the eddy kinetic energy at a given location. Basically, this is to underscore that non-locality is important for parameterizations. Parameterizations with prognostic eddy energy equations are pretty common in engineering turbulence. If any of you are familiar with computational fluid dynamics, RANS models, K-epsilon models, one equation, two equation models, these things all carry around prognostic equations for the small scale kinetic energy and energy dissipation rate and things like this. And so they're non-local. It's pretty common. In ocean modeling, non-local parameterizations are very uncommon. They've only been proposed in a couple of places as far as I know. So we have one from Eden and Great Lodge, which has actually since been kind of abandoned by Carson Eden. He may come back to it. And then Andy Maida and I proposed one recently in a very idealized quasi-geostrophic setting, which of course needs to be extended. And then David Marshall and his collaborators have advocated using non-local parameterizations. Also, I'll note that Schaefer-Smith Andy Maida and myself used multiple scale asymptotics in a paper in 2012. We actually predicted that the eddy energy budget is going to be non-local in certain parts of the ocean. So we have a theoretical prediction, we have the fact that we think this is important for parameterizations. Again, why else does it matter? In physical oceanography, it's very common to see doubly periodic simulations, studies of mesoscale dynamics using doubly periodic simulations, typically quasi-geostrophic. This is fairly common in atmospheric science as well. And the idea is that these doubly periodic simulations can be models of local patches of ocean. Of course, a periodic simulation, though, can only model a patch of ocean if that ocean has a local energy budget. Right? A periodic simulation has, by nature, a local energy budget. Any energy that gets generated in the periodic domain has to be dissipated in the periodic domain. That's not true in an ocean patch, and so there's potentially a mismatch there. And we show that later on there is, in fact, a mismatch. So, little background again, this is an atmospheric science paper, but Potvin and Held in '96 ran a channel simulation and then diagnosed the PV flux from the mesoscale eddies in the channel simulation. And then they ran doubly periodic simulations forced by the local mean shear from the channel, diagnosed the PV flux from that, and found that they're actually very close. So in their simulation, let's see, I believe the solid line is the result of the PV flux versus the PV, or the shear, from the doubly periodic simulations. And then the dotted lines are the empirical relationship found by comparing the PV flux in the channel simulation with the local shear. And this is strongly local, meaning you can use a doubly periodic simulation to predict the local properties of the eddies in this channel. This seems to imply that eddies are local, and people have, partly based on this and partly not based on this, I imagine, but people have really latched onto the idea of using doubly periodic models like this as local models of ocean. So they say if there's a local relationship between PV flux and a mean gradient, they argue that a doubly periodic model would be the appropriate tool for determining.
Just tell us what a double periodic model is.
Yeah, so you take it's a simulation, right? And it's not a square domain, but when you go out one side, you just come right back in the other. And when you go out that side, you come back in the other. And it's fairly simple to run those. You just use Fourier series, and you can use the FFT, and it's quite fast. Okay, so there have been a lot of doubly periodic simulations like this.
And the purpose is to avoid boundary condition problems.
That's right, yeah, you don't have any, well, you're avoiding also boundary currents, basically. It's just avoiding any complication that might be associated with having a boundary. So there have been a whole series of studies using these doubly periodic simulations, trying to understand mesoscale eddies. It's a burgeoning field. I've only cited a few of these. Of course, this only makes sense if the periodic simulations are good models of patches with local energetics. So in 2011, Antoine Bonai, Jeff Vallis, and Schaefer Smith tried to check, to some extent, the question, or check the assumption that doubly periodic simulations are, in fact, good models of patches of ocean. So to do this, they took an eddy resolving simulation of the Southern Ocean, primitive equation, the Meso project, which is from a paper by Hallberg and Nanadesky in 2006. And then they took little patches of ocean from this eddy resolving Southern Ocean simulation, and then tried to run doubly periodic models to see if they compared. Okay? And in some places it worked, and in some places it didn't. In some places, the doubly periodic simulations were good models of the ocean patch, and in others they weren't. And yes?
So how big are the boxes like the Southern Ocean? Is it the whole, around the whole globe this way?
It is, yeah. For this,
And then a range of latitudes?
That's right, yeah. There, the meso simulation, I believe, cuts off sort of part of the Antarctic continent. You don't get the whole coast of Antarctica, but you get part of that. And then it goes up to, I believe, the southern tip of Africa. And then it goes all the way around. Forced by just reanalysis winds, I think. And so their conjecture as to why some places worked and some places didn't is that in regions where you had the mean flow was unstable to Beroclinic instability. In these regions, you would get a good agreement with the periodic model. But in regions where you have actually a fairly weak instability from the mean flow, you would not get a good agreement with the doubly periodic model. And in essence, in those regions, you're expecting that the eddies are being convected in rather than being generated locally. They also had problems, though, in this setup because their Southern Ocean model is a primitive equation model, and their doubly periodic models are quasi-geostrophic. So it's possible that there was some mismatch, not due to locality effects, but just because of the fact that the dynamics in the different simulations were different. So that's my intro. Now, what do we do? Where do we fit into the picture? We're trying to directly measure eddy energy locality. We want to take an ocean patch, decompose it into a mean flow and an eddy flow, measure the budget, the energy budget for the eddies, and see if it's local or not. We choose to do this in a two-layer quasi-geostrophic setting in order to keep things simple, keep things clear. Naturally, you could do this in a more complicated setting. But the first thing to do, my background is applied math, so the first thing to do is to do the simplest problem. And then the other benefit of using QG dynamics is that we have a perfect comparison between our ocean, quote unquote, simulations with the basin and our doubly periodic patch simulations. They have exactly the same dynamics. So if there's a mismatch, we can't say, oh, well, the doubly periodic simulation is quasi-geostrophic, but the other one is primitive equation. That's why we've chosen to use two-layer QG simulations. These are the standard equations. We do have a free surface, but it has a minimal effect. It's the deformation radius associated with the free surface is so large that it doesn't really affect the dynamics. We run simulations in a square domain. It's extremely large, 6,000 kilometers on a side. Deformation radius is 20 kilometers, and we have an 8-kilometer grid. 1 kilometer upper depth, 4 kilometer lower depth. And then we run these simulations with 2 different wind stress profiles. We chose to use a very large domain like that so that we can have a good separation of scales between the large scale and the large scale domain and the small scale eddies. Okay, so here's a movie of the vorticity. Hard to see what's going on in the center of the domain. This is from the simulation with a purely zonal wind stress. So the wind stress is zonal. It's confined to the upper 91% of the domain, so there's no wind stress forcing down here, just to break the symmetry and make it a little more interesting. This is obviously a fairly strongly turbulent eddying region, but there are also regions down here. It's hard to see because of the color scale. But there are also regions near the bottom, near the top, where you actually have some nonlinear eddying turbulent dynamics as well. The fact that our domain is so large, 6,000 kilometers across, kind of makes it hard for you to get much eddies moving out there. So that's the one simulation with zonal wind stress. And then here's one with the non-zonal wind stress. So in this simulation, the wind stress itself is zonal, but it varies as you move across the domain. So you have a wind stress that sort of starts down here and then comes up and moves over there. And as a result, you don't just get a flat Gulf Stream across here. It kind of meanders up that way.
So what kind of curl is in the wind stress? What kind of curl?
So we just use a sine. Basically, it's a full sine wave across here, but then we start the sine wave down here, and then we translate it up here, and the total wind stress is 4 pascals, I guess. But it's a very large domain, so when you take the curl, you know, the 4 pascals gets divided by the width of the domain. I can't quote an actual number for the curl of the wind stress for you. This is just really to give you an idea of what the dynamics look like. So we have our simulations. They have large-scale parts. They have small-scale parts. When I showed you the vorticity field, that's basically just the small-scale parts. The large-scale part is a classical sort of double gyre, which extends throughout the whole domain. With this data, we need to now separate it into a large-scale mean and a small-scale eddy component in order to make progress with energy locality. Typically, what would be done is to do a time average. A zonal average is what you would use in a channel. Typically, you don't really use a zonal average in a basin, but these are common averages. There's problems with these averages, though. I mean, people use them, I think, because they're analytically tractable, they're computationally simple, but both methods actually fail to separate by spatial scale. So if you do a time average, and you have a large-scale Rossby wave, that large-scale Rossby wave is going to be part of the eddies, because it's a transient dynamic. But we're really interested in subgrid scale parameterization. We think of mesoscale eddies as being related to a certain spatial scale, not related to a certain time scale. So the time mean is not ideal. The zonal mean has the same problem. Also, a time mean, even though we have no topography in our simulations, a time mean would imply that there's no energy transfer between large and small scales, between mean and eddies, due to the topography, whereas in reality, topography can generate small scales, rectify small scales. It can have an interesting impact. So we don't use the time average, we don't use the zonal average. You could also use a Fourier series. So you take your data, you do a sine series or a cosine series, and then you just truncate the coefficients, and the large scale part is the mean, and the small scale coefficients go to make up the eddy field. The problem with that is that it's not a good measure for a certain patch. It separates things into large and small scales globally over the whole domain, but when you're interested in a specific patch, it doesn't do a good job of separating large and small scales for a specific patch. It is useful for other things. So what do we actually do? To define the large scale part of the field, we have our data field, it's PV. Q is the potential vorticity. Q sub I is PV in layer I. But for any variable, you can define the large scale part denoted by an overbar by inverting this elliptic operator. There's a variety of things we could have chosen. We could have done a local moving average, something like that. This operator was convenient because you have to invert this for the PV inversion, which is part of the quasi-geostrophic code anyways. So we already had a code to do this, and it was convenient to use it. So you define the large scale part by inverting this. The small scale part you define just by subtracting off the large scale part. The problem with this filter, and in fact with any filter in an enclosed domain, a domain with boundaries, is that it's inhomogeneous, meaning that it doesn't commute with differentiation, or as a result of its inhomogeneity, it doesn't commute with differentiation. This is just kind of a technical detail that makes the analysis a little bit harder, but not too bad. Okay. So we take our QG equations. We have a data set that's been generated by the QG equations. We know how to separate the data into a large and a small scale part. We want to understand the energy budget of the small scales. We do that by applying a high pass filter to the PV equations to get an equation that is satisfied by the small scale part of PV. When you do that, you have to commute the filtering with the derivatives. So whenever you commute the filtering with the derivatives, this would be, this prime should really go outside the divergence, but we move it inside the divergence, and that incurs an error. So every time you commute these derivatives, you get an error. we track those errors in the code to make sure that they're small. They're in fact localized in a very thin layer near the boundaries. This just shows that the fact that the error is small means that you can trust the filter to do what we expect it to do, to separate into large and small scale parts. Okay. So we have PV equations for the small scale part of PV. We derive the energy equation, as usual for QG, by multiplying by the stream function and performing some manipulations, integrating across the depth. And you get an equation that says the small scale energy is generated, fluxed, dissipated, and then you have a term for the error. Okay. This is the generation term. It's interaction with the large scales. So interacting with the large scales generates small scale energy. There is a piece also from the wind flux, or excuse me, from the wind forcing, because the wind forcing can formally have small scales, but this piece is actually very small in our simulations. All of the generation term just comes from interaction with the large scales. The dissipation term comes from Ekman drag and from viscous dissipation. And as I pointed out here, the generation term, even though I'm calling it generation, it can have either side. The interaction of the large and the small scales can send energy into the small scales, in which case generation is positive. Or you can have the eddies, the small scales, losing energy to the large scales, in which case generation is negative. So they can be, for example, sharpening the mean jet. And in that case, the generation would be negative. This is the form of the flux term, divergence of the flux. Okay, we would like to separate this out into pieces associated with different physical processes. Non-local energy flux could be related to wave radiation. It could be self-advection of the eddies. It could be advection by the large-scale flow. Although we would like to do that, it's not very clear how you can do that because of this term right here. So if you go and read if you read Pedlowski's book, GFD, 1987, he derives the energy flux for the QG equations and shows that this term here is related to the pressure flux. So if you derive the energy equation for the primitive equations, you'll see that there's a flux of energy associated with pressure. And that's related to this guy right here. And the pressure flux actually is involved in all of the different physical processes. The pressure flux is involved in wave radiation, self-advection, et cetera, et cetera. And there's no clear way to separate out what part of the pressure flux goes with what physical process. So unfortunately, we weren't able to figure out a good way to split this non-local term into pieces corresponding to different physical processes. I also want to mention that, as I was talking about earlier, because the generation term can be negative, in any region where the generation is negative, the flux has to be, or the total energy budget has to be negative here, negative for dissipation, and it has to be balanced by a flux, an incoming flux of energy from elsewhere. So in any region where the eddies are in fact strengthening the mean flow, the energetics cannot be local for that region. It can't be a balance between these two terms if they're both negative. On the next slide, I'll show you the results of our simulations, the diagnostics. So we evaluate the four terms, generation, dissipation, flux, and error, from our simulations. We then average them over 10 years to smooth things out. You don't have to do the average. The budget is defined instantaneously, but by doing an average, it smooths things out and gives you an idea of what's going on in different areas a little more clearly. And then also, there's a big variation in amplitude across the domain. You have, for example, very large generation in some regions, very large dissipation in some regions, and not in other regions. And so in order to make the pictures legible, we scale them. We scale the four terms by the local value of the energy. This is what you get. The left column is the simulation with purely zonal wind stress. The right column is the simulation with the non-zonal wind stress. Top row is generation. second row is flux, third row is dissipation, and last row is error. So the error is quite small, it's concentrated near the boundaries. How can we interpret these? So the first thing to notice is that in both of these simulations, the generation is positive, it's fairly strongly positive in these regions at the north and south. And that's balanced by dissipation. And the flux terms there are quite small. So white means it's close to zero. So those regions are actually strongly local. They have a local energy budget. In contrast, there's very little dissipation in this central region where the sort of Gulf Stream, the super idealized model Gulf Stream would be. And the generation is actually negative there, meaning that the eddies are losing energy to the large scale flow. The eddies are reinforcing the jet in this region here, in both simulations. It's a little bit harder to tell in here because we have some jet structures, but here clearly the generation is negative. And so that region has to have a non-local energy budget. And in fact, through this whole entire central region, the energy budget is non-local. So this demonstrates that in a very simple model, I don't think we've done anything tricky to make it unrealistic or otherwise rig the system. In this very, very simple model, there's a very large region where the eddy energy is non-local. Now, this is admittedly a very idealized study, but the fact that you have so much non-locality in this study suggests that in the real ocean there may also be a significant amount of non-locality for eddy energy. So this is the end of our diagnostics of the eddy energy budget, and then I'm going to go talk about how we tried to compare with doubly periodic simulations to see when they worked and when they didn't, and then we're going to relate that to whether the energy budget was local or not.
Yeah, just a question or comment here. So, why is that sort of surprising? Because people have been doing atmospheric energetics calculations for years, and it's been shown that atmospheric energetics is clearly non-local. So you have regions of storm track entrance where there's strong generation, but that energy is fluxed to the downstream regions where you have strong deep fluent flow, where the eddies actually dissipate. So in the atmosphere, it's clearly non-local. So
well,
you would expect similar.
I mean, I believe that that's the case, but when I was searching the ocean literature, I didn't see the references to that. I mean, it seems, from the standpoint just of the ocean literature, to be somewhat surprising. But I would appreciate to learn about those references. A lot of energetic studies have been done for the ocean as well, where you separate out the mean and eddies, and then you look at the energy budgets. But typically, those are done for an entire simulation. You'll do it for the whole globe or for your entire domain, integrating over the domain. And when you do that, you completely integrate out the flux terms, and you can't see if it's local or not. All you can see is the exchange between large scale and small scale. Okay, so doubly periodic models. We expect in the regions where the energy budget is not local that the doubly periodic simulations won't work. We can check this pretty easily. We use a very simple measure. We know what the eddy kinetic energy density is across our simulations, our basin simulations. So we run doubly periodic simulations driven by the shear that we get from our basin simulations over the entire domain, and then check if the eddy kinetic energy density matches between the doubly periodic simulation and the patch from the basin. And this is the basin eddy kinetic energy density, and this is the doubly periodic simulation. Each point on here is a single doubly periodic simulation. And you can see that there's not a very good matchup, especially in this central region. So there's two regions where it's really quite poor. In the central region, where the energetics are strongly non-local, you get a very poor agreement with the doubly periodic simulations. Also, along these lines here, you have a very poor agreement, but it goes the other way. In the central region, the eddy energy is way too low in the doubly periodic simulations. And along these lines, it's way too high. And that's related to the fact that the shear, along these lines, the mean shear is directly north-south. And it's in the opposite direction from the beta effect. And I'll talk about that more in a minute. Let's go back to the Antoine Vanay's paper. So their conjecture was that in any region where there was a strong instability, a strong shear, then you would see good performance of these doubly periodic models. And in regions where you had a weak shear, you would see poor performance. This is the growth rate of the Beroclinic instability from our simulations, zonal wind, non-zonal wind. And you can see that actually there's, these regions here where the doubly periodic simulations are most plausible actually have the strongest instabilities. So there's a good correspondence there. However, there's also these regions along here, these lines, where the doubly periodic simulations have way too much energy. That's not mentioned in this paper, and it doesn't correspond in any particular way to the strength of instability along lines through here. It sort of occurs at the borders of these two regions, of these different regions. Okay. So there is a plausible correlation between the performance of periodic simulations and the strength of the instability. But there's this place where the mean shear is strongly meridional, that the doubly periodic simulations don't work well. People have done doubly periodic simulations with a non-zonal shear going back to at least 2004. That's the earliest reference I know for doubly periodic simulations, where the shear is actually not zonally directed. This only makes sense in the ocean, I think. Most people in the atmosphere are thinking about a zonal mean, in which case the shear has to be zonally directed. In the ocean, though, you can get strong meridional flows, so people wanted to know what's the impact of that meridional flow on the eddies. And in this paper, they found that when you run these doubly periodic simulations with meridional shear, you get a huge eddy energy. And they interpreted this to suggest that even the weak mid-ocean gyroflows, because they're not zonally aligned, can generate a lot of eddy energy. So the idea being that eddies are generated through Beroclinic instability, even though the instability is fairly weak in these regions of meridional flow, the doubly periodic simulations generate a lot of energy. So maybe this goes back to the fact that eddies are generated by Beroclinic instability. And we actually find that the doubly periodic simulations with meridional shear just are not good approximations of patches of ocean. So it's you have to be very careful about interpreting the results of simulations that have a meridional shear as being related to patches of ocean, because in this model, they don't work, they don't correspond. Okay. Go back again to Pavan and Held. So they say that you can use these doubly periodic simulations to predict the PV flux. And in light of our results, if there is a relationship between the PV flux and the mean gradient, then yeah, the periodic models might work. In the places where we do have local energetics, this might be a good thing to pursue. But everywhere where the doubly periodic simulations don't match, which is to say where the energetics are non-local, we really don't expect these doubly periodic simulations to give us any insight into the structure of the PV flux. In summary, we run these simulations, we've diagnosed the energy budget, it's non-local over a big area. That's perhaps not surprising, but I think it's somewhat surprising for the ocean community. Doubly periodic simulations do not model regions with non-local energetics. That's completely what you expect. But because of the heavy reliance on doubly periodic simulations in physical oceanography, I think it's important to emphasize this point. It's possible that we could improve the doubly periodic simulations by using the time-dependent large-scale flow. So what we actually did is we took our simulations, took the large-scale mean shear and then time averaged it, and then ran the doubly periodic simulations with that. But you can actually run a doubly periodic simulation with the time-varying mean shear. If you did that, it might improve the results. There have been a couple papers, Poulin and collaborators in 2010. And then non-local energetics and weak instability are correlated, which was conjectured by Benai et al. So that's my summary. Thank you.
Questions for?
Could you help me understand, what is pressure flux? I mean, pressure is simply through the hydrostatic equation is a function of the water density and the depth. So, as a force per unit area, it's a scalar. So what does a pressure flux mean?
So it's not the dominant component of that part of pressure. The hydrostatic pressure is not the one that's primarily responsible for the pressure flux. It's the fluctuations of pressure that are associated with incompressibility, which is a good approximation in the ocean that's associated with the pressure flux. So if you just think of Navier-Stokes equation with no buoyancy density anomalies at all, you get the energy equation just by taking the inner product with U, and you get a flux divergence term. The U dot grad pressure, you can just rearrange into divergence of U times pressure, because U is incompressible, and that is the pressure flux. It's d by dt of energy is equal to a bunch of stuff plus a divergence of U times the pressure.
So can you explain in words what it does? I mean, why is it important?
I don't have much intuition about the pressure flux.
Say most things with wave radiation is all pressure flux.
Well, yeah, I mean, it's involved in all of these different physical processes. So wave radiation, when you look at the equation, if you ignore the nonlinear term even, and you're just dealing with linear waves, there's an energy flux associated with the Rossby waves. And when you look at that energy flux, one piece of it comes from the beta term in the equation, and one piece of it comes from the pressure term in the equation. The same thing if you ignore the beta term and just have the nonlinear equation. One piece of it comes from the nonlinear term, and one piece of it comes from the pressure term. So I don't have a clear interpretation of that term, but it does link all of the various processes together.
So, in the current global climate model, such as from the IPCC that you cited, where the localization assumption is prevalent.
Mm-hmm.
So, in your estimate, what kind of an error does it produce in the climate simulation overlog? Well, like, what is the most? Is there a significant? Where would we see a significant effect in the simulation? So that is my question. Like in the currents, like the simulation of the Gulf Stream, or where? I mean, do you expect the error because of this assumption?
Right. So one potential source of error, the way these climate models are run now, is you basically tune. You have a bunch of coefficients in your parameterization. It's all local, and you tune the coefficients in order to match the current climate as best you can. And then you run a climate change scenario with those tuned coefficients. But not when you change the climate, the structure of those coefficients will presumably change because of non-local effects. And so one potential impact of that is in the Southern Ocean. Under climate change, the wind stress over the Southern Ocean is expected to increase. In fact, it's been increasing since the 70s. And none of the current parameterizations are, okay, so the wind stress is increasing, but actually the transport, the zonal transport is not increasing. And in fact, none of the IPCC ocean models, the parameterized ones, can capture that. And we're currently trying to test whether a non-local parameterization will fix that problem with climate models. We think that's related to the non-local effects.
Thank you.
Yes?
I know you use idealized case, but can you come and just take North Pacific as an example? Where do you expect to see this local versus non-local? Just kind of, yes.
Right. So in the North Pacific, I would say the entire region around the Kuroshio and Oyashio is going to have non-local energetics. When you get closer to the equator and the return flow, the westward flow there, the southern half of the subtropical gyre presumably has more local energetics. I think that the subpolar gyre in the North Pacific is not terribly strong, so I'm not sure what to expect there.
So you're basically saying the region where you have strong wind forcing tend to be local, where you have the current tend to be non-local. Is that right?
It's
Kind of.
I think the non-locality in that region is related to the wind forcing, but it's I think more related to the fact that you have small scales that are being generated in the western boundary currents. I mean, that's actually just a thin current, and those things get advected out into the ocean, and the fact that it's set up that way is related to the wind stress, but it's an indirect effect.
One more question, sorry.
Yeah.
So when you say weak, is that 3K, what do you mean by weak? What that is?
The weak instability, right? Yeah, we have not tried to quantify some sort of threshold of, growth rate of the Beroclinic instability, which would demarcate a region of local versus non-local energetics. I think we could do that in this model, but this model is so idealized that it's not clear.
It's not clear what the physical process actually is.
You mean it's Beroclinic instability.
Yeah, I'm not really talking about stress, I don't really care. See, the thing that worried me a little bit is that, you mentioned the place could be selective in terms of generation, but it could be two big terms subtract each other, let's say.
Yes. So the generation could be negative as a result of cancellation.
Yeah, so that's kind of question that
Right. No, we haven't tried to address that sort of question. Just like we didn't split up the pressure flux, or split up the non-local term. We didn't split up the generation term. We did split out the wind piece, but other than that, we didn't split it into a barotropic instability versus a baroclinic instability.
Can you do that, or you have the same kind of problem as the first one?
We may be able to do that. I think we'd have more luck than with the pressure flux.
Sorry,
Yeah, I sort of have a conceptual question here. So in your work sort of suggests sort of there's a big separation between local and non-local energy budget. But it's well known that actually the energy budget is not unique. So you can actually rewrite the energy budget by changing terms where you can actually change the conversion term and add flux term. So the flux and energy flux and conversions are not unique. And Adam Plummeter has written a paper sort of suggesting that energy budget is not unique. You can change all the conversion and fluxes completely by just rewriting terms.
Mm-hmm.
So I've been struggling with that. I look at energy quite a bit also. And how would you sort of reconcile that? Because here you are using one specific form of the energy equation, which when derived in the linear limit, you can justify it. Because in the linear limit, the energy flux is equal to the group velocity times the wave times the energy. But once you add shear and once you add all of the nonlinear terms in it, you can't really justify that this is the unique form of the energy budget. And if you rewrite it, then your local becomes non-local, and you could.
Yeah, that's right.
Yeah.
So let me back up at the energy budget itself here. So there's two issues. One of them is that the flux here is, we're taking the divergence of the flux. And so in some sense, the flux of energy itself is not clearly defined because it's, yeah, you can always add a non-divergent flux term to this. We avoided that problem by just not dealing with the fluxes directly, but only with their divergence. So that the degree of, as soon as you start trying to look directly at an energy flux or at any kind of a flux that you've diagnosed, there are problems associated with the fact that you can always add a non-divergent term to it and the divergence remains the same. We avoid that. The other problem, though, is that the generation term here, you can always rewrite this by taking it and writing it as a piece plus the divergence of something else. And there's an infinite number of ways of doing that. And as you said, we stuck with this way because it's the one in the linear limit that makes the most sense.
But there are infinite number of formulations that actually reduces to that in the linear limit.
Right, but none of those are particularly, none of those seem to be obviously better than this one. And this one,
yeah, but this one is not obviously better
clear
than no, because, for example, Plum's example is actually you use it using the sort of traditional Eulerian mean.
Right.
But if you use the transform Eulerian mean to write the budget, then it's completely different, and the interpretation of all the terms and the locality of the budget is actually completely different.
Yeah, so take these results with a bit of a grain of salt, because the way that you interpret things is as being a generation term or a flux term, et cetera, is not always completely clear. We did have some internal struggles with that when we were writing this paper, and failing to come up with a really obvious choice, we stuck with this one. That's the best I can say.
Probably one more question. Maybe we should adjourn to lunch. I don't know who got their hand up first.
Go ahead.
Who wants it first?
Okay. Could you go back to your two-layer model?
Yeah, just the equations?
Yes.
Okay. Yeah.
You used the deformation radius as 20 kilometers somewhere.
Yes, 20 kilometers, that's right.
Yes. How this number was determined, or is just an estimate, or is continued to the model?
I don't remember that actually. Sorry. There we go.
Okay.
So it's a QG model, so the deformation radius is the same over the whole domain. I'm not trying to imply that you don't know that. Just explaining here. And when you set up the model, you put in your coefficients for your density difference across the layer and the depth of each layer, et cetera, and then from that you just directly compute what are the external and internal deformation radius. And it's not exactly 20, it's like 19 point something, but yeah, that's how we determined it.
Does that mean the base at this on this scale or close to this scale will be most important to this model, or at the same time most important to the
Yeah, so the eddies are pretty much, the eddies themselves are a bigger scale than 20 kilometers. That's pretty common in a two-layer model like this. The radius of the eddies is anywhere in our model from 60 to 100 kilometers. But the way that we do our separation of large scale, small scale, using this PV inversion, we set the filter, this filter scale separates out between large and small scales. And we set that filter scale to be a radius, quote unquote, of 180 kilometers. And that's 1 over a wave number. So the wave number would be, the wavelength would be 2 pi times that. And we also used a very large domain in order to try to get a clear separation between, really large scale gyres and whatever the Eddy's scale happens to be between 60 to 100 kilometers, we should get a clear separation between those by setting it up the way we did.
We should probably thank the speaker and then go to lunch. And if you still have questions, you can ask them there. Give me the wrong for lunch.
Hopefully I won't have to find my